Video for Math 98, we will look at problems covering section 14.1 and 14.2, which goes over homework number 8 in the course. These problems that we're going to discuss are like problems 13 through 18 on the homework. Let's remember something from Math 93. In Math 93, we talked about a system of equations. So here we have equation, I'm going to call this equation 1 and equation 2. And these were two linear equations, meaning they are just lines when you graph them. So you might have a picture like this. And the solution to this system was their point of intersection. And you might remember from Math 93, they didn't all have solutions. Sometimes there was no solution. Sometimes the two lines were identical, and there were every solution. So we had two methods of solving these algebraically. One was called substitution and one is called elimination. With substitution, you take one of the equations and solve for one of the variables. That means I could take equation number 1 and solve for y or for x, or equation number 2 and solve for y or for x. Now since the coefficient, the number in front of x is 1 in equation 1, I'm going to use equation 1 and solve for x. So how do we do that? I'm going to subtract 2y from each side. So I get x equals minus 9 minus 2y. Now, as the word substitution implies, I'm going to substitute minus 9 minus 2y for x in the other equation. So I'll write the second equation down here just for our reference. 4y minus 3x equals 12. And I will substitute for x minus 9 minus 2y. Now, to solve this, finish this problem, all we need to do is solve this linear equation. You should be good at that by now. This becomes 4y plus 27 plus 6y equals 12, which becomes 10y plus 27 equals 12. And let's move up here. That gives you, excuse me, I forgot my y there, 10y, okay, equals minus 15. So y equals minus 15 over 10, or minus 3/2. Now, you're only halfway done. This is the y-coordinate of your point of intersection. To find the x-coordinate, you can use one of the original equations or this simplified equation to find our value of x. So you would substitute the value of y into one of these equations. Because it's easier, I'm going to use this one. So if I use that one, I get x equals minus 9 minus 2y, but y is minus 3/2. Doing this arithmetic, you get x equals minus 9 plus 3, which is minus 6. So my point of intersection is minus 6 minus 3/2. If you check this point into the original equations, you will see that it works. And that was called finding a solution to a system of equations. Now, in Math 93, we always dealt with linear equations, equations that were lines. In the past few weeks in this class, we have dealt with equations that are not lines. For example, look at this system, which is called a nonlinear system. We have y equals 2x squared minus 3x minus 5, which is a parabola, and 2x minus y equals 2, which is a line. To solve this using substitution, we're going to use the same method. We're going to solve one of these for one of the variables and plug it in to the next one. Now, if you look closely at this system, you'll see that the first equation is already solved for y. It already has y alone. So I'm just going to substitute the first equation into the second. So instead of 2x minus y equals 2, I'm going to write 2x minus the quantity 2x squared minus 3x minus 5 equals 2. If I simplify this, I get 2x minus 2x squared plus 3x plus 5 equals 2. That gives me minus 2x squared. 2x and 3x is 5x. plus 5 equals 2. If I continue to simplify by moving the 2 over to the left-hand side, I get this. Now, I don't know about you, I sure don't like this being negative, so I'm going to multiply both sides of this equation by -1. That will give me 2x squared minus 5x minus 3 equals 0. This is a quadratic equation. I'm now going to solve this quadratic equation for possible solutions. So to do that, I need to factor. And we're looking for the factors of -6 that add up to 5. That would be -6 and 1. So this gives me the solutions 2x plus 1 equals 0, or x minus 3 equals 0. And this gives you the solution 2x equals -1, or x equals -1/2, or x equals 3. Now, notice there are two values here for x. That means there are two places that this parabola and this line intersect. Does that make sense? Before I finish this problem, let's take a look on my calculator at what this would look like. Okay? So if I take a look at my calculator of what this would look like, I'm going to go over to y equals, clear out what I have. I'm going to put in the first equation, 2x squared minus 3x minus 5. And the second equation, I would have to solve that for y. If I do solve that for y, it ends up being 2x minus 2. Now, if I take a look at this at a standard window, noting what my answers are, I think this will work. I have my parabola, and I have my line. And you can see there are 2 points here where this intersects. One seems to be at 3, and one seems to be at about -1/2. So it's possible, a system of equations with a parabola and a line, for there to be two solutions. It's also possible for there to be one solution. Maybe the line just touches it at one point. Or it's also possible for there to be no solutions. Perhaps the line and the parabola never touch. So this is a little interesting. It's not quite like linear systems where you always had one solution, no solutions, or infinitely many. There's more possibilities here. To finish this problem, I need to find the value for y for each of these. I can use either of my original equations, this one or this one, by substituting the value for x I found in to find the value for y. Now I'm just going to use this one, so I'm going to say 2x minus y equals 2. If I plug in the value -1/2 for x, that's going to give you -1 minus y equals 2. So minus y equals 3, or y equals -3. So one possible solution is -1/2 -3. Another possible solution, if I use x equals 3, and I use 2x minus y equals 2, is to say 2 times 3 minus y equals 2, 6 minus y equals 2, minus y equals -4, so y equals 4. So the other possible solution is x equals 3, y equals 4. How does this jive with our picture? Well, let's go back to our picture. There's a little trick I can use on the calculator to help me verify my answers. If once I have my equations plotted and I've set my window so that my points of intersection show up, I can find these points of intersection by hitting second trace and then going over to intersect, and I'll get first curve, second curve, and a guess. And this is my first point of intersection. Notice that is -1/2 and -3. To find my second one, I'm going to do this again. Do second trace for calculate. Go to intersect. Just so you know, I'm going to move my little spider guy here on my parabola. That's my first curve. Here's my second curve. Now I get guess, and you can see guess is important here. I need to be closer to the point I want. I want this point up here. I am closer. So if I hit enter, I get the point 3, 4. So that is a way to solve a nonlinear system. Let's take a look at another example. In this example, we have two parabolas. I have this one here and this one here. Now this parabola is already solved for y, so I could again plug that in to this one and just get a solution. For this time, though, just to be a little different, I'm going to take this equation and I'm going to solve it for y. The easiest way to solve for y is to add y to both sides. When I do that, I get this equation here. So now I have my two parabolas. They're both solved for y. So I'm going to replace y with x squared plus 4 in the first equation. Now let's continue on. You're probably pretty good at factoring by now. I'll subtract x squared from each side, and I'll subtract 4 from each side. And I get this equation. Solving this quadratic equation, again, I think this can be factored. Factors of negative 10 that add up to 3 are positive 5 and negative 2. That tells you that x plus 5 equals 0, or x minus 2 equals 0. So x equals negative 5, or x equals 2. Now I can use this equation to help me find my possible solutions. So if x equals negative 5, that would be negative 5 squared plus 4 equals y. So 25 plus 4 equals y. So this would be negative 5, 29. And this one, x equals 2, I'm going to replace in this equation again to help me find y. That's 2 squared plus 4 equals y, or 4 plus 4 equals y, or y equals 8. So my solution is 2, 8. Now, to do this on my calculator, just to check, I'm going to go back to y equals, hit clear, type in my first one, which was 2x squared plus 3x minus 6. And my second one, which was y equals x squared plus 4. Remember, to use your calculator, equations must be solved for y. My window isn't going to be appropriate here. You might notice that my solutions were negative 5 and 2. So for x, I probably want to go a little bit smaller than negative 5. I might go negative 10 to 10, still count to 1. Y, negative 5 seems reasonable, but I went all the way up to 29. So let's go to 35, and let's count by 5s this time. If I draw a graph, there's my first parabola, there's my second, and you can see there's a point of intersection here, and if you look closely, there's a point of intersection here. So I've got 2 points of intersection. One looks like it's about at negative 5, and the other one looks like it's about at 2. To find these exactly, I'll use the calculate menus, second trace, intersect. First curve is 2x squared plus 3x minus 6. Great. Second curve is this. Now I need to get closer to my point. I'll get closer to this one first. If I do and hit enter, there's my 2, 8. Doing that again, second calc, intersect. First curve, you'll notice, is my 2x squared plus 3x minus 6. I'll move it over here so you can see that. My second curve is x squared plus 4. And my guess, I am closer to this one, so it should find that point, minus 529 for me. Let's take a look at this one. Here we have one of our conic sections, a circle and a parabola. Now before I do this, I'm going to try to just sketch this by hand. The circle, if you remember your stuff from section 14.1, this is a circle, center 0, 0, and radius 2. So I'm going to, I'm sorry, not radius 2, radius 4. I'm going to just draw this circle out for you. Not a great artist, as you know, but there it is. And what about this parabola, x squared minus 4? Well, you know the parabola y equals x squared, and this is going to have its vertex down here, and this is actually going to come up kind of like this. Okay, that's a very approximate drawing. But this shows you that this possibly could have 3 points of intersection. How would that show up algebraically? Well, you'll notice that this is already solved for y. You could plug y in there, but we will get a mess because x squared minus 4 squared will give me kind of a mess. I think what I'd like to do is I'd like to substitute not for y, but for x squared. So I'm going to take the first equation, and I'm going to add 4 to each side and get x squared equals y plus 4. Now, replacing this into the second equation, I'm going to eliminate x squared and just write y plus 4 plus y squared equals 16. That gives me y squared plus y plus 4 equals 16. Remember, this has to be 0. Subtract 16. Y squared plus y minus 12 equals 0. So y plus 4, y minus 3 equals 0. That gives me possible solutions for y of negative 4 and possible solutions for y of 3. So those are my possible solutions for y. Now to find x, I'm going to use this equation right here. So when y equals negative 4, I have y plus 4 equals x squared. So negative 4 plus 4 equals x squared. That gives you 0 equals x squared, which of course gives you the answer that x equals 0. So one possible point is 0, negative 4. Another possible point, if I let y equal 3, I get 3 plus 4 equals x squared, or 7 equals x squared. So x equals what? Well, if you remember, it's plus or minus the square root of 7 by taking the square root of each side. So that gives you that x could be plus the square root of 7 and y can be 3. And x could be minus the square root of 7 and y can be 3. If you look back at our original drawing, you see that this kind of makes sense. Here's square root of 7, 3. Here's minus square root of 7, 3. And here's 0, negative 4. So this is basically the idea behind solving systems of nonlinear equations. Let's do some harder ones. This one looks very threatening. And again, these are solved for y, but it might be easier for you to substitute the 2 to the x in this case right there. So you don't have to substitute the y by putting that right there. It's not wrong to do that. But I could certainly write this as y equals 5 minus y, because 2 to the x equals y. That gives you that 2y equals 5, or y equals 5 halves. Okay? If y equals 5 halves, then using my first equation, I can get that y equals 2 to the x, so 5 halves equals 2 to the x. Now remembering your work in chapter 13, this problem is going to involve logarithms. Log 5 halves equals log 2 to the x. Allows you to bring the x down. And when I do this all, I get x equals log 5 halves over log 2. Now let's take a closer look at this one on my calculator. First of all, I want to calculate that value log. So you hit your log button. 5 divided by 2 divided by log 2. And this is approximately equal to 1.3219 if I go out to 4 decimal places. So my approximate solution is 1.3219, 5 halves. Now taking a look at this on my calculator, I'm going to clear this out. I have 2 to the x, and I have 5 minus 2 to the x. Okay, I'm going to just use a standard window here of, let's say, minus 5 to 5 on my x, and I'm going to go minus 10 to 10 on my y, counting by 1. There's 2 to the x. There's 5 minus 2 to the x. This point right here, okay, looks like it could be 1.3219. Let's calculate that with intersect. First curve, second curve, guess. Here we go, 1.3219, and y equals 2.5. So we have, again, another linear system of equations. This one. The little trick here is to think about this as 4 to the x times 4 to the 4th. Now that gives me the equation y equals 4 to the 4th times 4 to the x. Now you may say, well, I sure don't like 4 to the 4th. That's fine. Go use your calculator and you'll figure out that 4 to the 4th is 256. So this is 256 times 4 to the x. The second equation is y equals 16 plus 4 to the x. So we have these two equations. And again, I think it's a little easier to substitute for 4 to the x. And I'm going to use this equation and solve for 4 to the x. By subtracting 16 from each side, I get that. Then I replace that in the original equation, 256 times y minus 16. That ends up y equals 256y minus 16 times 256. That answer is 4,096. Simplifying this, that's 255y minus 255y by subtracting 256y from each side. That leaves me with negative 4,096. So my final answer is this, 4,096 divided by 255. Now, to find the answer for x, well, that's pretty easy. 4 to the x equals 4,096 minus 255 minus 16. Okay. Remember, use your logarithms, and there's no reason to turn this into a decimal to start with. Your calculator can do all this calculation for you. Just leave it exact, like it is right now. Then bring the x down and divide by log 4, and here's your answer. Log 4,096 over 255 minus 16 over log 4. Now, using this calculator to do that, I'll say log 4,096 divided by 255 minus 16 divided by log of 4. That ends up, that x is approximately minus 2, but we'll say minus 1.997. And y is this value, and that is your point of intersection. One last problem, which involves logarithms. By now, you see that this is already solved for y, and that it's pretty easy for me to write this second equation as y equals 1 minus y, because log 2x equals y. That gives you 2y equals x, or y equals 1/2. So 1/2 equals log 2x. That tells you that 2 to the 1/2 equals x, so that's square root of 2. So my solution here is square root of 2 1/2. So this problem looked a lot more threatening than it is. That is the point of intersection between these two problems. I hope you have found this video useful.